ಕಿರಣ್ ಮಾತಾಡ್ತಾನೆ ಮಧ್ಯಾಹ್ನ ಚಲೋ. Good morning. Welcome back to the class. So today we'll see the last topic in your unit number 1. That is a mathematical model which we have left out. So this is a mathematical model of armature controlled DC motor. Now here, before starting this, you should have some basic idea about a DC motor. In DC motor, it is a direct current motor. Direct current motor, as you know, there are two types of motors which are commonly used. One is DC motor, one is AC motor. In AC motor, there are two types once again, that is AC induction motor and AC synchronous motor. So AC motor, there is one advantage that in a induction motor, there is no power supply.
Excuse me, sir. Your voice is breaking.
Voice is breaking. Is it clear now?
Yes, sir. Clear, sir.
Yeah. Then see, in AC motor, there are two types. One is AC induction motor and AC synchronous motor. So the AC motor, there is one advantage. That means in a motor, you know, there are field windings to generate the magnetic flux, whereas there is an armature winding which is used to generate the torque. See here, in any motor which works on a Faraday's laws of electromagnetic induction. Wait 1 minute, I will bring the cord. I think it will help. Is it clear now? Just answer. I'm using hands-free. Is my voice clear now?
Yes, sir.
Yeah.
Yes, sir.
Okay. So in AC induction motor, as in any electrical motor, there are two things. One, you have to generate the magnetic flux, and second, you have to supply the power to a armature or electricity so that the motor will start running. So in small motors, you might have seen some toy motors which you see during in childhood days. You can see a very small motor driving a small car or something like that. It is in that if you break open that motor, you will find a magnet there. So these are called as permanent magnet motors. As the amount of flux required is small, a permanent magnet can be suitable for that. But if we go for large amount of power for motor, in that case, a permanent magnet, you cannot use it basically because it will be very bulky, one thing, and it will be extremely expensive. So normally, permanent magnets are not suitable. The permanent magnets have advantages. The advantage is that they doesn't require any power source. But the disadvantage is they will be expensive and bulky. So for any large motor, the field is generated by a electromagnet, not by a permanent magnet. So when the electromagnet is used, so there is a separate power supply for that field winding or for that magnet, that is called as field winding. Whereas armature winding, in that case, that is one which is going to rotate. So in AC induction motor, the induction takes place and automatically to the armature, and naturally for armature there is no power supply. So the advantage, see, if you see any AC induction motor, there are armature rods or armature wire which is not connected with any power source. So the induction takes place because of Faraday's laws of electromagnetic induction. So rotor rotates freely without any power supply. That is the advantage of AC induction motor. Whereas AC synchronous motor, there is a certain modification is done, and because of that you will get a synchronous speed. That means a fixed speed. So it depends upon the frequency of the power supply. So normally you get RPM of, depending on the, there is a equation for induction motor, that is 120 F divided by P, where 120 is a constant, F is frequency of power supply. So that means, suppose in our KEB power supply is 50 Hertz, then it is 120 into 50, that is 6000, divided by P, that is number of poles. If the number of poles are 2, then the RPM is 3000. That is because 6000 divided by 2. Whereas if you have a 4-pole motor, in that case it is 6000 divided by 4, 1500. So naturally you might have seen in the market, most of the induction motor either will have 1500 RPM, 750 RPM, 3000 RPM, or so on, like that. So they are used when you require a constant speed. So induction motor is used in olden days when there is a constant speed requirement is there. But when you want to have a variable speed motor, the problem with the AC motor is that here the torque generated by the motor, the torque, you know the power equation, 2 pi nt upon 60. Power is equal to 2 pi nt upon 60. If that means power is directly proportional to N into T, where N is the RPM of the motor and T is the torque produced by the motor. Now here, if the power has to remain constant, if you increase the speed, the torque will decrease, because the power output of the motor has to remain constant, because it is depend on the supply voltage and the power rating of the motor. So here what happens is, basic problem is, if you try to reduce the speed of the motor, the torque will not increase in AC induction motor, and thereby which the power also comes down. Similarly, if you try to increase the speed, the torque reduces at much faster rate, and hence the power decreases further. So AC induction motors, in normal cases, by controlling power supply to the motor, you cannot control the speed. That is the basic drawback of AC induction motor. Nowadays, you will get a variable electrical drive, which is an induction motor only. That is due to some other technology, that is called as inverter technology, what you have come across. Now if you buy a new refrigerator or new air conditioner, you come across the term called as inverter drive. The inverter drive means not the inverter one which you use for a conversion of AC to DC in your home or DC to AC in your home. See, inverter here means what it does is, it is variable frequency drive. So in early 70s, when the power electronics was not developed much, in those days variable frequency drives were not possible. So now variable frequency drive is possible, basically because what it does, because of the inverter technology, the device used here is SCR, or silicon controlled rectifier, or thyristor. Thyristor drive motors you come across. So the advantage of that is, first what they do to change the frequency. See, KEB supplies you a constant frequency of 50 Hertz. You have no control over it. So what they do, these inverter drives, what they do, they first change the frequency to AC to DC. So first they use a rectifier and convert AC power supply, say 230 volts AC is converted to 230 volt DC by using a rectifier. And after that, using a silicon controlled rectifier and by using some switching techniques, they can change that back to AC. And while converting it to AC, they can convert it to a different frequency what it is required, because the equation, as I said, it is 120 F divided by P. So the number of poles, once you are fixed, you cannot change it. So naturally that cannot be changed. Only way is to change the frequency. So instead of 50 hertz, if I make the frequency as 100 hertz, then the speed will get doubled. So this variable frequency drives were possible after 1980s. Even in 80s also, the cost of the thyristor drives were very expensive and used for only certain traction purpose, like in locomotives and all. Even till recently also, Indian Railway used to use the DC drive only. Even today also, till 4 years back, the most of the local trains in Mumbai used to run by a DC drive. DC series motors were used in that. So reason is that electronics circuitry were not easily available or very expensive. But nowadays, because the whole drive system has become so cheap, so that even percolated down to a small devices like your refrigerator and air conditioner, which is not costing more than 15 to 20,000 rupees. So that is now being commonly adopted, and because of that, DC drives are totally out. So, but still then, for our lab or something where the cost is important, we still use a DC drive. For example, you might have in your 7th semester you might have done experiment on. Now you are going to do the experiment on what is known as this governors and all. In that governors, to change the speed, we are using a DC motor, which is DC armature controlled DC motor, which is a variable speed device. So this is one part. Now coming back to our,
Hello,
yes,
excuse me, sir.
yes, yes, tell me.
Sir,
Yes.
sir, your voice is breaking, sir.
So that is a network issue then. 1 minute, I will check the network once again, because I am using whatever is possible. So is it connected to Wi-Fi or something? Mac तुला connect झाले ते. 1 minute, huh? It is connected to Mac. Now, can you hear me clearly without voice problem?
Yes, sir.
Okay. Earlier it was,
Yes, sir.
yes, it was earlier connected to Wi-Fi because of low speed. It was creating problem. Now there should not be any issue. So here if you see, as far as the DC motor is concerned, see here in DC motor there are number of types. Basically the two types are separately excited or excited in combination. There are two types. Separately excited means the motor has separate power source for generation of the field, that is magnetic flux, and there is a separate source for armature which is going to rotate. So one thing is there that in a DC motor, when the armature is supplied with the power, when it is supplied with the power, it is rotating. When to supply the power to a rotating part, you require what is known as some slip rings. Slip rings are given so that the rings rotate along with the armature, whereas the brushes connect the ring, and so that the power is supplied to the armature. At the same time, another disadvantage of DC motor is the power source is DC, so its direction is constant. So what happens is the motor rotates through 180 degrees and once again it reverses back. So that means you will not get a complete rotation, only half rotation is possible. So what is done here is what is known as commutator is used. Commutator is nothing but a slip ring, but divided into two half parts, one top part and one bottom part. When the top part is there and the bottom part is there, that two parts, what happens is in one side there is a positive line and another side there is a negative line. So after completion of a half phase, the brushes will change the position. So one which was connected to positive now gets connected to negative, and one which is connected to negative gets connected to positive. So the direction reversal takes place and motor continuously starts rotating. So this process is called as commutation. So that commutation is integral part of any DC motor. So this is what is separately excited motor. So other combination type, there is a DC shunt motor, DC series motor, DC compound motor, that we are not interested at present. Basically, I will just give you the idea what is in DC shunt motor. That means the field windings and armature windings are parallel to each other. That means there is one single source of power and the field winding is connected in parallel with the armature winding. So whereas in series motor, armature and field windings are in series, whereas in compound motor, part of the field winding and part of the armature winding is in parallel and in series. So each one of them has certain advantages and disadvantages. Like DC shunt motor has low starting torque, but it is safer, whereas series motor will have a high standing torque, but it is slightly unsafe. Compound motor falls in between the two. It has both advantages and disadvantages of shunt and series motor. So each one has its own application. DC shunt motor is commonly used for most of the common applications, whereas DC series motors are used when you require a very high starting torque, like EMU trains or local trains of Bombay. They have a AC series motor. That means you might have seen the EMU train catches the speed on the platform itself. It is for quick stopping and quick starting. This arrangement is there. But the long distance train, which move very slowly on the platform and they gain the speed over a time, in that case, the DC shunt motors are used. So forget that. Now we are coming to the separately excited motor. In the separately excited motor, there are two types: armature controlled DC motor and field controlled DC motor. In armature controlled DC motor, we are supplying power to the armature and changing the voltage supply to the armature, and thereby which changing the speed of the motor. And we are keeping the power supply to the field. This is a field. You can see this is a field winding which generates the magnetic flux. That is constant. That is kept constant. This power supply is kept constant, but armature winding power supply is EA. A stands for armature. EA, that can be varied. If you change the voltage supply to the armature, the speed will change. This is what is the principle. So we are going to model it. So this is the symbol of a armature, and this armature has winding. Winding means wire. That wire will have a resistance RA, and it has a inductance LA. That is modeled here. It is resistance RA and inductance LA. And this goes into the armature windings of the motor, and supply voltage is EA. And because of that, there is one rotary mass which having a J as moment of inertia connected to this. So we have to model this now. We are now keeping field current constant. We are keeping the field current constant, and we are going to change the armature current IA. So this is what is the principle. Now see here, IA is the armature current, IF is the field current, we have kept it constant. EA is supply voltage to the armature. EB is the back EMF. Let us come to that later. Tm is the torque developed by the motor. Theta is angular displacement of the shaft or the rotor, and J is equivalent moment of inertia of the motor along with the rotor, and F0 is the damping provided, or a frictional damping at the bearing and the rotor. See here, similar to Kirchhoff's laws are very much similar to Newton's laws of motion. So there is one law called as Lenz's law, which is equivalent of Newton's third law of motion. That is, for every action there is equivalent opposite reaction. That means what happens is, when you supply the power to the motor, so the motor rotates. Motor rotates means what? It will draw the power from the source. So here there is a drop of voltage taking place in the rotor, and that drop of voltage is nothing but a back EMF, which is it depends upon the rate of change of flux. It depends upon the rate of change of flux, and rate of change of flux depends upon the speed of the motor. So this back EMF indirectly depends upon the speed of the motor, or omega of the motor, that is dx by dt of the motor, or d theta by dt of the motor. So you can model it further. So first is the flux. Flux is Kf into If. We are keeping constant. Then torque generated by the motor is Kf into If into Kt into K1 into Ia. That means Ia is the armature current, If is the field current, and these Ks are two constants of proportionality. But out of which we are keeping the armature current field current constant. If we are keeping constant. So all constants I will club into Kt. And so the torque generated by the motor is equal to Kt into Ia. So whatever is the armature current multiplied by one constant of proportionality, that much torque will be generated. That is equation number 2.48. Then where the Kt is known as motor torque constant. Similarly, the back EMF, as I said, is proportional to rate of change of flux, or indirectly it is proportional to velocity of the motor, where velocity of the motor is omega or d theta by dt. So the constant of proportionality between back EMF and the velocity of the motor is Kb. So this is Kb is back EMF constant. So Kb into d theta by dt, this is another equation 2.48. Now I can write down the, for the circuit, I can draw the equation. See here, this is our circuit. EA is the supply voltage. So EA is equal to voltage drop across resistance plus voltage drop across inductance plus voltage drop due to back EMF. This plus this plus this is equal to supply voltage. That is what is the equation here. This plus this plus this is equal to supply voltage. So supply voltage is equal to drop of voltage across inductance, which we have seen in an electrical circuit, LA into DIA by dt, where I is the current, IA is the current. So rate of change of current multiplied by inductance is drop of voltage across inductor plus voltage drop across resistance is Ra into Ia plus back EMF, that is EB, which is from the formula 2.49, which is equal to EA. So coming to that, you can write down the equation for that rotor now. So this rotor has polar moment of inertia J. So the inertia component plus damping component is equal to torque. So for a rotor, the supply is torque, that is Kt into Ia Tm, and it is due to that the drop of torque takes place due to J into d theta square, d square theta by dt square, that is J into alpha, that is angular acceleration. So J is like a mass, m into a is this equation. Similarly, it is J into d omega by dt, or d square theta by dt square. So that is one. Second one is due to damping or a friction. So it is B into V. So B into V is replaced by F into V is omega here, because it is rotating. Omega is d theta by dt. So this is another equation. This is a mechanical equation. That is another one is for mechanical system. This is a equation for electrical system. That previous equation is there. So back EMF value is Kb into theta of S. S theta of S, because I am taking the Laplace transform here. You can see here, this is EB is equal to Kb into d theta by dt. If you take the Laplace of this, it becomes EB of S is equal to Kb, d theta by dt is there, so S into theta of S. So this is what is the equation it becomes. So EB is equal to Kb S into theta of S. Similarly, if you take a Laplace transform of that electrical system, this becomes LAS into IA of S, because d by dt is there, RA into IA of S. So I will write it here like that. That is LAS into RA, I of S I am taking common, is equal to EA minus EB, that is Tm, and this is one equation. And second equation is, if I take a Laplace transform of this, Js square into theta of S, Fs into theta of S is equal to Tm, that is Kt into Ia. So theta of S, if you take common, it becomes Js square plus Fs. So this is another equation. So overall, you get the transfer function theta of S upon Ea of S by simplification as Kt divided by this, or this can be done by using a block diagram. See here, first equation you can see here, Ea minus Eb of S is equal to LAS plus Ra into Ia of S. So Ea minus Eb, Ea, here Ea is there, here Eb is there. Ea minus Eb, when it gets divided by LAS plus Ra, LAS plus Ra, this whole thing gets divided by LAS plus Ra, you will get Ia. You will get Ia. This is one equation. Whereas if you see that second equation for rotor, here IAS is available now. That has to be manipulated by this factor. So you can see that IAS is available here. That is Kt divided by S into Js plus F. Kt divided by S into this, I will take it here. Kt divided by S Js square plus Fs is equal to theta of S. So that I have taken here. So you will get the output. So if you join them together, Ea, Eb, this one, here Ia is available, this will go to this block and it will come out. See, this is this block and this is this block. Theta is coming. Theta into Kb of S is Eb. So this is a back EMF. Eb is theta into Kb into S as per your equation. So that is a feedback loop. So this armature controlled DC motor, looking at this system, you can solve this block diagram and get the answer. One way is to solve these equations and get the answer. Second way is to solve this block diagram and get the answer. From block diagram, it is very clear that it is a closed loop system, because here you can see there is a feedback. So the advantage of armature controlled DC motor, what is the advantage of feedback is, see what happens here, that back EMF acts as a regulator. So the back EMF depends upon the speed of the motor. If the speed of the motor increases, back EMF increases. When the back EMF increases, this EB increases. When this EB increases, EA minus EB decreases. So the power supply of the motor, if the speed goes up, gets reduced. So in normal cases, suppose if this feedback is not there and the coupling between the motor and that rotor is broken, so what happens is, as the load is suddenly removed, the motor speed goes on increasing, and as there is no feedback, the motor will keep on rotating with higher and higher speed. Finally it may explode. But that will not happen in armature controlled DC motor, because the speed will never go beyond certain limit as the set value by you. Whatever value you have set, depending on that you have chosen EA. So higher the voltage, higher will be the speed. Lower the voltage, lower will the speed. What speed you want? Hello. Can you hear me? Or any trouble with the internet?
No, sir. Yes, sir. It is good.
Okay. So I will come back to the presentation. So looking at this, the advantage of armature controlled DC motor is that it is a closed loop control system, and here the speed never reaches beyond the set value. So depending on the set value, you have to select EA. So suppose for 100 volts power supply, so you are getting 1000 RPM. So if it is 150 volts, then it may be 1500 RPM. I am taking linear consideration. It may not be actually true. So what happens if you want a motor to run at 1000 RPM, you set EA to say 100 volts. See, this is an empirical equation. That calculation is just, I am giving one example, not true. That is for 100 volt, you will get 1000 RPM, 150 volts to 1500 RPM, nothing like that. Just I am giving an example. Suppose you want the speed to be 1000 RPM and you have selected corresponding to 1000 RPM, the supply voltage is 100 volts. So you have reduced the voltage 230 volts to 100 volts and supplied here. So once you supply it here, initially what happens, the motor is at the rest. When the motor is at the rest, the speed is practically zero. When the speed is zero, this back EMF is also zero. So full 100 volt supply is given to the motor, and the motor RPMs gradually goes on increasing. Once it goes on increasing, as the theta goes on increasing, when the theta goes on increasing, the back EMF goes on increasing. So the power supply to the motor, EA minus EB, goes on decreasing. So this will happen till the motor speed reaches the desired value of say 1000 RPM. If suppose there is a slightly reduced load reduces. If the load reduces, what happens is the speed increases. When the speed increases, the EB increases. So the further power supply to the motor reduces. So once again the speed starts decreasing. So speed is automatically maintained constant to the set value. This is the greatest advantage of the armature controlled DC motor. And 99% of DC motor variable speed drives using DC motor are invariably armature controlled DC motor, basically because it is the closed loop system. This is the advantage of this motor. So we'll take a break now, and in the next class at 11 o'clock I will go for DC shunt motor, field controlled DC motor, and thereby which you will come to know how that motor is what you call a non-feedback type or open loop system. So if you have any questions, you can ask me. If you have not understood something, you can ask me in chat box or by unmuting your mic. So application of armature controlled DC motor or field controlled DC motor, where you want a variable speed drive at a very cheap rate. For example, in our lab, as I said, almost all lab, there is a design lab. Wherever we are using a variable speed drive, for most of the cases, like say governor experiment, it is DC armature controlled DC motor only. Basically because it is very cheap and where the losses we are not much bothered about. But when you come across losses, DC drives are not preferred over AC drives. Reason is the losses in DC drives are always higher. Any DC drive, in olden days, if you remember in our childhood days, earlier DC power supply used to be there in Belgaum. But over the years, KAB changed it to AC. Reason is the losses in AC are much lesser and the DC power supply is slightly risky. In case of a electrical shock, there is a sudden guaranteed death, whereas in the case of AC, this one, what happens is because the continuously the polarity is changing, so you not get stuck to that wire. If you by chance you come in contact with the live electrical wire, you will be thrown away, you might have seen, only because of shock person dies. Whereas in DC, it is like a getting a, what you say, under the say in rainy season or when lightning hits. When the lightning hits, there is a sudden death, guaranteed death, basically because it is a DC. It is a static electricity and it doesn't have a polarity. It is one directional current only. So naturally, the death is certain. Whereas in AC drives, you are generally, by chance, if you touch a live electrical wire, there is a greater chance that you are thrown away. And for 230 power supply, death is very rare. Only 440 power supply in three-phase current, the chances of death are higher. Basically because your body is a non-conductor or a bad conductor and resistance is very high and hence you get burnt rather than local burning will take place. So DC drives were olden days, almost all 100% of the DC drives were used in olden days. But now because of advantage of power electronics, after 1980s, most of the heavy drives where the cost is not important is AC.